Just when you thought you were out, we bring you back in. Asymptotes. They never go away. And we get closer and closer and closer to them. And boom, they never go away. They're always there, man. Asymptotes. We've talked about vertical asymptotes. Those are the values that make the denominator of a simplified fraction equal 0, right? The x values that make the denominator of a simplified fraction equal 0. We've talked about a hole in the graph, which seems like it could be an asymptote value, but it's not. A hole in the graph happens not when you get undefined, but when you get 0 over 0, right? You get indeterminate form. So when you plug in a number and you get 0 over 0, you have a hole in the graph. That means that x value would cancel out, basically, right? You'd have a fraction and you could simplify the fraction, and those factors that do cancel out, those are the factors that would give you a hole in the graph versus a vertical asymptote. Okay, so they're kind of like cousins. Today we're going to talk about horizontal asymptotes. So I thought it'd be good to look at the vertical ones again real quick, because all of this is sort of connected. You got to know the differences. So if you didn't write these notes down before, it might be good to pause it right here and write these down. I made some examples real quick for us to kind of look at together. So before we get into horizontal asymptotes, right? Just when you thought you were done with asymptotes, we're back. Question 1 and question 2. Notice they look kind of alike. Question 1 has an x minus on top that question 2 does not have. So what does that mean? Well, both of those problems, 1 and 2, have a denominator that factors, right? X squared minus 4 factors into x minus 2x plus 2. For example 1, the x minus 2's cancel out. So when the factors do cancel out, that's when you have a hole in the graph. So for problem 1, there's a hole at x equals 2. Notice the rest of problem 1 here. Once you cancel out, oops, wrong button. Oh, why is this not working? Martin, hold on, I have the graph turned on. Bad teacher. When you cancel out the x minus 1, in the numerator you have a 1 left over, and then the fraction simplified version becomes 1 over x plus 2. And negative 2 makes that denominator equal 0. So negative 2 has a vertical asymptote. So VA is vertical asymptote. Problem 2, very similar. You factor the denominator, but notice the x minus 2 does not cancel out like it did on problem 1. Oops, circle the wrong part. Because there's no x minus on top, right? It's just 2. So example 2 has 2 vertical asymptotes. There aren't any holes in that graph because no factors cancel out, okay? So you can see how with these rational functions, these rational equations, they're the ones that have very weird very weird properties. With like a parabola, it's always a parabola. When you have an x squared, it's a parabola. If it's a negative x squared, well, it opens down, but it's still always a parabola. When it comes to rational functions, they can vary so much. So we're seeing that just here from example 1, example 2. Example 3, we can out an x in the denominator, and the x on top cancels with the x on the bottom. So there's a hole at x equals 0. Right? The number that makes the factors that do cancel out equal 0. That's when you have indeterminate form or 0 over 0 or a hole in the graph. There'd be a vertical asymptote at 3 because x minus 3 does not cancel out. Number 4 had a whole lot of factoring. You can an x out of the top and the bottom, right? The common factor on the top and the bottom of x. When you factor out the x on top, you have an x squared minus 9, which factors into x plus 3x minus 3. When you the x out on the bottom, right, when you bring out the common factor, you have x squared minus x minus 12, and negative 4 times positive 3 makes negative 12, and 3 minus 4 makes negative 1. So there's an x plus 3 factor that cancels and an x factor that cancels on question 4, and you're left with a vertical asymptote at 4, right? Notice there's 2 holes in 4. So problem 4 has 2 holes in it and a vertical asymptote. Problem 2 had no hole, but it had 2 vertical asymptotes. So these things can be very crazy and strange, but that's how they work, okay? So in class, this would have been a whole lesson by itself, and we pretty much covered this lesson, and I just wanted to review with you. So here are 6 problems that I want you to practice. Notice the questions go down 6, 7, 8, 9, 10, 11. Okay, so find the vertical asymptotes and find the places where the graph has a hole or indeterminate form. Okay, the x values. Give the x values of the vertical asymptotes, the x values for the hole. So you're going to work these problems out and you're going to pause the video right here. Okay, pause the video because now I'm going to bring up the answers. So pause the video and work these out. Okay, cool. Boom. That was quick. Oops, sorry, wrong button. Here are the answers. 6, 7, 8, 9, 10, 11 go across more than down. Changed it up. Honestly, you can just pause it here and look at these answers. I don't know that I need to talk through all of them. One of the things you might notice is on 6 and 7, I use the phrase end form or indeterminate form as abbreviation. And then 8, 9, 10, 11, I use the word hole. Okay, so whenever there's a hole in the graph, that means the function equals the indeterminate form there, right? So on problem 6, there is no hole in that graph. Problem 6, there is no number for x that makes that function equal 0 over 0. Okay, that on 6, there is no number that makes it 0 over 0. Even when you plug in 0, you get 1 over 1, right? What's the vertical asymptote? That's the value that you get when you set the denominator equal to 0. You find the value of x that makes the denominator equal 0. So I literally set it equal to 0, subtract 1, divide by 3, you get negative 1/3, right? So vertical asymptote and indeterminate form. 7, there's no vertical asymptote, but there was a hole in the graph. So 6 and 7 are kind of like complete opposites, right? 7, no vertical asymptote, but there's a hole at 4 because the factor x minus 4 cancels out. And so if x equals 4, you get 0 over 0. So number 8, you can an x out on the denominator, and then that cancels out one of the x's on top. So that means there is a hole at 0. Now, a quirky thing about 8, the denominator will never equal 0. See if I can highlight that. So I've got my cursor here. See a little red dot. X squared plus 1 never equals 0. If you set that equal to 0 and solve for x, you get x equals plus or minus I. And on a real number plane, I doesn't exist. So number 8 would not have a vertical asymptote, even though there's an x in the denominator. Okay, so just having an x in the denominator is not bad. It's whenever that x has a value, has a number that would make the denominator equal 0. That's when it's bad. So 8 has no vertical asymptote, but it has a hole in it. I think I have one like 8 coming up in a little bit, actually. X over x squared plus 1. So remember that. 9, we can an x squared on top, and then the denominator factors into x plus 2, x minus 2. And notice nothing cancels out. There's no common factors on the top and the bottom that cancel out. So there's no hole in the graph, but it has 2 vertical asymptotes, kind of like the example we saw in the previous part. 10, you factor the top and the bottom, there's a hole at -1, vertical asymptote at 4. 11, you can a 2x out of the denominator, and then x squared minus 4 factors again into x plus 2, x minus 2. On top, you can a 5 out, and you get an x plus 2. So x plus 2's cancel, meaning there's a hole at -2, because -2 plus 2 makes 0. So the factors that do cancel out equal 0 at -2. So there's a removable discontinuity at -2, or there's a hole in the graph at -2. Okay, so there's 2 vertical asymptotes, because see the 2x in the denominator means that at x equals 0, there's a vertical asymptote. At x equals 2, there's a vertical asymptote. So all of that, I don't know how long the video has been. It's been like 10 minutes already. I forget. There's only been 5. I don't have a timer going, and I forgot to look. I think it's been maybe 5 minutes. But what I really need to move on to with us today, in the here and now, are horizontal asymptotes. That's what today's lesson's all about. That's the title of this video. So I got to jump back over on it here. Horizontal asymptotes. So my first thought was, hey, maybe I should start with times that we've seen a horizontal asymptote. Okay, because a lot of functions don't have horizontal asymptotes, just like a lot of functions don't have vertical asymptotes. But we've seen a couple that do have horizontal asymptotes. And here you see example 1 and 2. Pretty much the same example. now that this is rolling, I'm not going to change it. But I could have put an example of exponential growth up here. I did 2 examples of exponential decay. One of them, I moved the horizontal asymptote up. Example 1, you see the horizontal asymptote is at 2. Whereas example 2, the horizontal asymptote is at 0. If you have exponential growth, it still has a horizontal asymptote. But we see the asymptote as we go backwards more, right? With exponential growth, the graph goes up. As x gets bigger, y gets bigger. But when you go to the left, as x gets more negative, so here we are going to be looking at horizontal asymptotes mostly as x gets bigger. So that's kind of, I guess, what I had in my mind. But like example 1, you have a half x plus 2, right? Remember, it's decay because 1/2 is less than 1, right? When it's less than 1, it decays. Example 2, e to the negative x. Well, remember, a negative exponent means you take the reciprocal of the base. So the reciprocal of e to the negative 1 power, is the same thing as 1 over e. And 1 over e is less than 1, right? 1 over e is like 0.4 or something. So exponential decay, the graph goes down. Notice on example 1, there's a plus 2 at the back, right? This plus 2 shifts the whole graph up above the x-axis too. So I have a horizontal asymptote at 2 on problem 1, whereas on problem 2, the horizontal asymptote is 0 because the x-axis is the horizontal asymptote, right? And that's going to happen a lot. The x-axis is a horizontal asymptote for a lot of functions. But another example of a horizontal asymptote was the tangent function. Sorry, arctangent function. I'm just looking at the word tan and forgetting about the arc in front of it. Inverse tangent, right? Or arctangent. In case you forgot, maybe or here, look, I'm gonna squeeze in an example before 3. What comes right before 3? 2.9. Remember, the tangent function is really sine over cosine. So you go back to our definition of asymptote, vertical asymptote. Remember, it was the values for x that make the denominator of a simplified fraction equal 0. Okay, so here's just a quick little sketch of the tangent graph. And the tangent graph has cosine in its denominator. And if cosine is ever equal to 0, that means tangent has a vertical asymptote. When does cosine equal 0? I don't know, it's tough to know that off the top of your head because you're not being able to look up at the poster. If we were in the room right now, we could look at the unit circle poster and we go, oh, when cosine is pi over 2, it equals 0. So at pi over 2, tangent has a vertical asymptote. That would be this one right here. And negative pi over 2, tangent has a vertical asymptote. And so when you find the inverse tangent, like example 3, or arctangent, right? Remember, the inverse function is when you reflect it across y equals x, and the graph ends up like flipping across y equals x. All of the vertical asymptotes would become horizontal asymptotes. Isn't that exciting? And we can't have like an infinite number of like tangent functions stacked on top of each other, or arctangent functions, because it's not a function, right? So we talked about all this way back in chapter 1. We saw the arctangent function a long time ago. So what we have to do is we just define arctangent to be between negative pi over 2 and positive pi over 2. Remember, it's from like the bottom of the unit circle, the fourth quadrant, around to the first quadrant. Negative pi over 2 up to positive pi over 2. That way it's a continuous function, right? This is a continuous function. And if I ask you what's the arctangent of 7, I go over here, 1, 2, 3, 4, 5, 6, 7, and I find that answer, okay, which I would need a calculator to do. But what's the arctangent of 1? Oh, well, that's pi over 4, because that's when tangent equals 1. So pi over 4 is an easy answer to know in your head without a calculator. But what I'm getting at is arctangent has 2 horizontal asymptotes. 2. And so as x gets bigger and bigger and bigger, notice the graph is approaching some constant value. The graph is like plateauing, right? It's flattening out to reaching some sort of limit. Okay, so we haven't really defined a horizontal asymptote. But that's what it is, right? Not all functions have horizontal asymptotes, but the ones that do, right? The horizontal asymptote, it is. Remember if you go back and look at your definition of, sorry guys, I'm trying to get this right. Definition of vertical asymptote. The vertical asymptote, remember, was the x values or value. Okay, it's possible there's more than one, right? So the x values. For a horizontal asymptote, it's just the opposite. The horizontal asymptote is the y value that the function is approaching, right? It's the y value that the graph is limited toward, if that makes sense. The y value are values that a function approaches, usually as as x goes to infinity, or negative infinity. Okay. It just depends on the equation. Like if I go back to example 1, what happens as x gets smaller and smaller and smaller? Well, the graph goes up, so it doesn't approach a horizontal asymptote as you go to negative infinity. But as you go to positive infinity, as x gets bigger and bigger and bigger, then it reaches some value. The arctangent function, as x gets bigger and bigger and bigger, notice it gets closer to pi over 2. This doesn't happen as I look at 0, or if I look at even where x is 1 or where x is 2. Right? At small values of x, I don't notice that there's a horizontal asymptote at play. Right? The horizontal asymptote usually shows up at the ends, towards the end of the graph. So let's rip through horizontal asymptotes then. How do I know when I have horizontal asymptotes? These are 2 examples that we've seen before that are kind of quirky, kind of unique. Okay. First thing I did here was I made a bunch of examples where there is no horizontal asymptote. And I just went ahead and sketched them and wrote the answers. The parabola, y equals x squared, right? If you're asked, what is the horizontal asymptote for y equals x squared? There's nothing funny about that, right? A parabola doesn't have a horizontal asymptote. A parabola never has a y value that it's like flattening out and approaching, right? As x gets bigger and bigger and bigger for the parabola, y just gets bigger and bigger and bigger and goes to infinity, right? Y goes up and up and up and up and up as x goes up and up and up and up. And even as x gets smaller and smaller and smaller, y gets bigger and bigger and bigger. So not all functions have horizontal asymptotes, just like not all functions have vertical asymptotes. Okay, if it's any kind of polynomial, x squared or x to the third or x to the seventh plus 2x to the fourth minus 3x cubed plus 12, right? Any polynomial function doesn't have a vertical or horizontal asymptote. That's what polynomials don't have. So there's no horizontal asymptote. I abbreviate vertical asymptote, VA, horizontal asymptote, HA. And if it's not funny, there's nothing funny, it's sad. See? No. Cosine function doesn't have a horizontal asymptote. It doesn't even have a vertical asymptote, right? As x gets bigger and bigger and bigger, the cosine function just keeps going up from 1 to -1 and then back up to 1 and -1. And it never reaches, the y value never approaches any sort of limit. Right? Y just changes from -1 to 1 forever. So there's no, oh, what did I do? I did something. There we go. And then I thought of a different one, the natural log function. The natural log function does have a vertical asymptote, and you might have forgotten that. This is something that we graphed. I'm pretty sure this was like right after winter break. We did, we talked about vectors and complex numbers, and then we went into logs and exponentials. So this was maybe somewhere in February. The natural log function does not have a horizontal asymptote. No, nothing funny about it. Okay. As x gets bigger and bigger and bigger, the natural log function goes up and up and up and up. It goes to infinity. Okay. But it does have a vertical asymptote. And we can ask that question. This could be a potential limit question, maybe on your next limit test. What is the limit as x approaches 0 from the right of the natural log function? And that's not one that you can really like algebra, like what you can do is you can plug in 0.1, plug in 0.01, plug in 0.001, get closer and closer and closer to 0 from the right, and you'll see the numbers just get more and more and more negative. If you have this picture in your head of the graph, like if you know what these graphs look like, that helps so much. A lot of times when it comes to like limits or calculus, I'm going to make a little sketch, like draw a picture. It helps. Because when you see, oh, there's a vertical asymptote, the left side of the graph goes down forever. So the limit as x approaches 0 from the right of natural log of x would be negative infinity. That's kind of like something I could have asked that question last week when we did vertical asymptotes. I didn't think about it, honestly. But maybe it'll be on the next quiz. So these are examples of no horizontal asymptote. So when do you have horizontal asymptotes other than these two that we talked about before? Exponential functions and log functions, or sorry, exponential functions and arctangents. Here are some examples of horizontal asymptotes. And the graphs are not drawn because I want to draw them with you. Because this is how you kind of see them happening. And I used a little graph maker here in this thing, which is, I don't know, it's whatever. Maybe it's better than me drawing it by hand, but still. Let's pick, okay, I'm on blue. Let's start with this one, slightly less complex. 1 over x. 1 over x is a rational function. Huh? Notice number 9, also a rational function when you have a fraction of functions. This is when you see a lot of horizontal asymptotes. Okay? Notice neither one of these, 8 or 9, is an exponential growth or decay. Neither one of these is an arctangent, right? It's not a parabola and it's not a cubic function. It's not any of those other things. These functions are rational functions, fraction functions. And these are the kind of functions that have vertical asymptotes, but they also have horizontal asymptotes. Okay, so what I decided to do was like hold off on the limit stuff. We're kind of put limits on pause for a minute. I just want to talk about how you know when you have horizontal asymptotes. That will play into our next section on limits. Okay, so just making a quick sketch of these graphs. One thing that we know automatically about 1 over x is it's a simplified fraction, right? You can't reduce it anymore. And so what number would you plug in for x to make the denominator equal 0? Because what I'm getting at here is, what is the vertical asymptote? The vertical asymptote would be the number you plug in for x to make x equal 0. So set up a little equation, x equals 0, and then solve it for x. Oh, what do you know? X equals 0. So there's a vertical asymptote, and knowing that is like super duper important, right? Knowing where the vertical asymptote like helps you quite a bit. And so now let's just plot some points, and maybe we start with positive points, and we'll take positive blue points, and let's pick 1. Plug it in for x. What does y equal when you have 1 over 1? Well, y equals 1. So there's a point at 1, 1. Let's let x be 2. What's 1 over 2? Well, 1 over 2 would be like 0.5, right? It'd be a half. So I got to go only up a half. Go to 5. What's 1 over 5? 1 over 5 is 0.2, right? So I went from 1 over 2 is 0.5. Did I say that right? And then at 5, I get 0.2. So 1/5 is 0.2. 1/2 is 0.5. And, you know, I don't, this thing wouldn't let me go out to 10. Ideally, I would go out to 10, because what's 1 over 10? 1 over 10 is 0.1. This goes to 9, and 1/9 is 0.9999999, which is really, really close to 0.1. Or 1/9 is 0.1111111. Sorry. It's just above 0.1. But what I'm getting at here is, you see in this example number 8, it's kind of like example 1. It's kind of like a exponential decay function. As x gets bigger and bigger, y gets smaller and smaller, right? Let x be 100. 1 over 100 is 0.01, right? That's a penny, 100th, 0.01. Let x be 1,000. I don't have a graph big enough here to do that. But if x is 1,000, it's 0.001. And so as x gets bigger and bigger and bigger, y is getting closer and closer and closer to what number? Ta-da! To 0, right? So it appears that, if I get out my handy dandy red, I think asymptotes are best drawn in red. It appears that there is a horizontal asymptote at the x-axis. The blue curve is going to get closer and closer to the x-axis, but it won't actually touch it. Okay, it gets closer and closer and closer to it. Horizontal asymptote. Looks like y equals 0 is a horizontal asymptote. Y equals 0. It's the y value that the graph is approaching as x goes to infinity, right? As x gets bigger and bigger and bigger, y is approaching 0. And it will never touch it, right? This blue curve that I just drew in here, it never actually touches the x-axis. It never crosses the x-axis. It just gets really close to it, okay? Forever closer and closer to it. And what happens if I go from 1 to 0. See, I got a big space in here that I haven't talked about yet. Well, there's a vertical asymptote, so you probably think, well, it's just going to draw it up. And that's exactly what it does, right? Pick a number between 0 and 1, like 0.5 or a half. What is 1 over a half? 1 over a half means you multiply by the reciprocal, right? And you get 2. So 1 over a half is 2. That would put the dot here. When x is 0.5, y is 2. Pick 1/9. What's 1 divided by a ninth? 1 divided by 1/9 is 9, which puts the dot way up there. And 1/9, remember, was 0.11111111. So it's very, very just barely over from 0. 0.11. It's barely over from 0. If I went to 1/100th, which is 0.01. So I'm going to go from the origin over 0.01. It's really hard to do that, right? The dot would be all the way up at 100. So this graph is bounded by these two asymptotes, a vertical asymptote and a horizontal asymptote. And it just makes a sharp kind of U-shaped curve. We've actually seen this curve before. Didn't think to mention that earlier, but give me a second. Now let's look at the negative numbers. If you plug in -1, right, you get -1. When x is -1, y is -1. If x is -2, y is -0.5 because it's 1 over -2. And 1 over -2 is -0.5. And so as we go backwards towards negative infinity, it does work that our horizontal asymptote is still back here, okay? We just happen to be down in quadrant 3 now because 1 divided by a negative is a negative. So since x is negative, turns out y is also negative. And if I were to pick a number like -1/9, then the dot would be at -9. So the graph goes like that, kind of two U-shaped graphs back to back. We've seen this before. We've seen this graph before when the asymptotes were diagonal, and now our asymptotes are horizontal and vertical. So it's definitely a different kind of hyperbola. But one of our first videos that you got to watch, right, during this whole shutdown time was on hyperbolas. We were finishing up the conic sections. Remember, the hyperbola was x squared minus y squared equals 1. Or like y squared over 4 minus x squared over 9 equals 1. It had x squareds and y squareds. So you notice this hyperbola in example 8, it is a hyperbola. It's not hyperbola in a conic form, completely different form of a hyperbola. Okay, so some rational functions make hyperbolas. Okay, not all of them. Like when we get to number 9 is also a rational function, but it's not a hyperbola. Completely different thing. So this is what makes rational functions so exciting. Sometimes there's vertical asymptotes, sometimes there's not. Sometimes there's holes, sometimes there's not. Sometimes you get a hyperbola, sometimes you don't. Sometimes you get a line with a hole in it, right? You could get a parabola with like an asymptote in it, kind of shape. Weird things can crazy happen with rational functions. But this is a hyperbola with a vertical and horizontal asymptote. And the horizontal asymptote is at y equals 0. And how do I know that? And it's because as x gets bigger and bigger and bigger, so thinking about this fraction, because this concept is actually huge, right? This number 1 over x, as x gets bigger and bigger and bigger. Like, for example, if I have a pizza, and I'm very happy to eat this whole pizza by myself, but one of my friends shows up and is like, yo, bro, what's up? And I'm like, dude, come in, have this pizza with me. Let's split this pizza. We'll go twosies on a pie, right? Halvesies. We're gonna go halvesies on a pie. So we get to split this pizza into 2, and we each get a half of pizza. That's not so bad, right? And then all of a sudden there's another knock at the door, and like 10 more friends showed up. And now you've gone from splitting your pizza into 2 and everybody gets a half to, well, 10 more friends are there. Now you have to cut the pizza into 12ths, right? And each one of you gets a 12th of the pizza, okay? And then it turns out all of the United States shows up. Well, how about a third of the United States shows up? If you have to cut a pizza into more and more and more slices, the same pizza, okay, one pizza cut into more and more and more slices, each slice gets smaller and smaller and smaller. The portion that you get gets smaller and smaller and smaller. And to the point where if I have to share a pizza with the whole world, I'm only going to get like a molecule of cheese. and that's not very yummy. This one little molecule of, can you even have a molecule of cheese? Is that a thing? I don't know. We need Coach Thompson in here. But still, this idea, when I have this fraction 1 over x, what is happening is that the denominator is growing, but the numerator is not. Okay? And so when that happens, the overall value, the y value, gets smaller and smaller and smaller. Right? It's like, imagine having a bunch of money in the bank and you pull some out, and then you pull some more out, and you keep pulling some more out, right? Cutting off hunks of what you have, the value gets less and less and less. So, okay, I'm talking too much. We got to get through these notes. I got one more example, and then I have notes. Because, how do I know? That's what I'm trying to build up to. So notice on number 9, my thought here on number 9 was that I want to have a fraction where the numerator does not stay the same. See, over here on example 8, the numerator was 1. There was no change in the numerator. But what I did do on number 9 was I made it so that the denominator changes at a bigger power or a bigger rate. Because this is really what it's all about. It's all about thinking about the numerator versus the denominator, comparing the numerator and the denominator, and basically which one grows faster, okay, or which one grows slower. That's what matters. And so for this example, notice this is the problem that showed up earlier when we reduced some fraction that was in the example you had earlier. Vertical asymptote is the value that makes the denominator of the simplified fraction equal 0. This fraction is simplified. I cannot factor or cancel anything. So what number makes the denominator equal 0? Is there a number that makes the denominator equal 0? There is no number that makes the denominator equal 0. Right? If I plug 0 in for x, 0 squared is 0 plus 1 makes 1. If I plug in a negative number, when you square it, it becomes positive. If you plug in a positive number, when you square it, it's still positive. Whenever you add 1 to any positive, it's more positive. So the denominator of this function never equals 0. So this is different than number 8. There is not a vertical asymptote. But what is the horizontal asymptote? It will have one of those. And how do I see it? Well, let's just plot some numbers. You notice I made my y value go up to 1 and down to -1. And so for a second, let's just plot a couple of points. Like I said a second ago, plot 0. I plugged in 0. Remember, I got 0 plus 1 in the denominator is 1. But what's 0 on top? 0 over 1 would make 0. So there is a dot at 0, 0. 0, 0, the origin, is a value here. So now let's pick another number like 1. When you plug in 1, right, on top, you got 1. What's 1 squared in the bottom? 1 squared is 1 plus 1 makes 2. So when I plug in x equals 1, I go up a half. And a half would be like, the middle right there, I guess. Undo. Put it right about there. Okay. And then let's let x be 2. When I plug in 2, what is 2 over 2 squared is 4 plus 1 is 5. 2 over 5 is 0.4. So if I go to 2, I'm going up 0.4. So this is 0.5, 0.4, 0.3, 0.2, 0.1, right? This is 0.5. 0.4 would be right there. When x is 2, y is 0.4. And then let's go just jump out to 9. Okay, kind of bored with this. When I go to 9, let x be 9. What is 9 squared? Oh, 9 squared is 81. 81 plus 1 is 82. Kind of yucky, right? What is 9 divided by 82? Well, 9 divided by 82 is like 1/9, really close to 1/9. Because 9 over 81 would be 1/9. 1/9, as we said earlier, is 0.111. So this is close to 0.1. I can get out a calculator and check it, but it's close to 0.1. So at 9, I'm like 0.1. If I were to plug in 10, you would get 10. Or 10 squared is 100, and 100 plus 1 is 101. So 10 over 101 I know is less than 0.1, because 10 over 100 is 0.1. If I have a bigger denominator, it's smaller. That's the whole point of this whole lesson is bigger denominator, the number gets smaller. 10 divided by 101 is actually. So what's happening is this graph is going, and you know what? I don't really like those like lines I drew there. Oh well. This graph goes up like this, very bizarre, and then back down at some point. It curves down. 1 comma a half is the highest point on the curve. So let x be 100. At 100, right, you get 100 divided by 10,001, which is like 0.001, or even less because it's 10,001. So this graph does appear to have a horizontal asymptote, right? As x gets bigger and bigger, it looks like it's flattening out to 0, just like number 8 did. Okay, now what happens when you plug in the negatives? Is it bad to have a negative? Well, when I plug -1 on top, I get -1. -1 squared plus 1 is +2. A -1 over +2 is -0.5, which would be -0.5 down here. And all the same points are going to show up. -2, I'm going to get -0.4. It's just they're negative now. Kind of like they did over on the blue curve on example 8. It's like the same numbers, but in the third quadrant. And if I go to -9, I'm going to be like -0.1111. So what is happening with this graph that's kind of funky? Oh, Martin, that wasn't very good. I don't like either of those, actually. Kind of makes me want to get out my handy dandy calculator. There we go. That's good enough. This is a funky graph. This is not a hyperbola. Okay. But what is also something that's happening here that's kind of crazy and kind of like you're thinking not supposed to happen is, so it's good to see this right now. And I'll mention it, and maybe you're still paying attention. This has been, what, 20, 30 minutes? Okay, I'm almost done, I promise. I really am. We have notes and then your homework. These are my 2 examples. The rest is just notes and, well, other examples. I don't have to work them out. They're already there. Sorry. What is happening here that's kind of different and new is that this graph does cross over the asymptote. This graph crosses its asymptote right here in the middle. And I've had a lot of students, even in AP Calculus, you get to AP Calculus and they're like, wait, I didn't think a graph could ever cross over its asymptote like this one does. And that's just because, like, in your brain, like, you have it, asymptote is an imaginary line. The graph gets closer and closer and closer to it, but it never touches it. And that is true. See, what's happening is as x gets bigger and bigger and bigger, the function gets closer and closer and closer, so the asymptote never touches it. But back in the middle, right, back at the center of this thing, it's not behaving like an asymptote. Okay. Now, when you have a vertical asymptote is definitely more, the graph isn't going to cross it. A vertical asymptote is a value for x where the function doesn't exist. Okay. So here for this one, y does exist at 0, and that's okay because it's still a function. But for a vertical asymptote, it can't not have an x and have an x. It can't be both, right? Unless you define it to be a piecewise function, you throw the x in there. It's a different thing completely. But this graph has a horizontal asymptote at 0. Okay, the first graph had a horizontal asymptote at 0, and you're seeing 2 very different types of horizontal asymptotes. You're seeing 2 very different flavors of rational functions. This is why I actually love rational functions, because you just never know what you're going to get. I don't know the name of this curve on 9. I'm sure it has some sort of name to it. It's kind of cool. It might be fun to type it in a graphic calculator and see it. Look better than mine, probably. But the overall concept here that we're trying to get at is, how do I know my rational function has a horizontal asymptote at 0? Okay, it's happening in both of the examples because the denominator gets bigger faster than the numerator does. Okay, another way to think of it is the numerator doesn't grow as fast as the denominator. So when the numerator is smaller than the denominator, and by numerator, I explicitly mean the power of the numerator in these examples. Okay, so for x to the first power on problem 9, the degree is 1. Remember that word, degree? The denominator's degree is 2. It's the highest power of the polynomial is the degree. When the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is at the x-axis. Okay, going back to example 8. Notice example 8, you might say, well, it doesn't even have an x on top. And that's because it's x to the 0, and x to the 0 is 1, and 1 times 1 just makes 1. So why write x to the 0 when I can just write 1? It's just less writing. The denominator's degree is 1. Notice 0 is less than 1. 1 is less than 2. When the degree of the numerator is less than the degree of the denominator, that's when your horizontal asymptote is at the x-axis or at y equals 0. So for horizontal asymptotes and rational functions, okay, first of all, you would think, when do I have horizontal asymptotes? A lot of times you don't have horizontal asymptotes. They show up with exponential growth and decay graphs, and they show up with inverse trig functions and other functions as well, probably that we haven't seen or learned about yet. But when you have a rational function, and this shows up so often in AP calculus, this concept right here, this rule number 1, if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0, which is also called the x-axis. And I put some examples here in red. I don't know, so I went through and I did not erase all the powers from the last time I did this. That sounds fine, that's fine. So this is like 1 over x. This is like, we just did that example, so I don't know that I need to even write those in there again, right? 1 over x, the degree of the numerator is 0, the degree of the denominator is 1. 0 is less than 1, so it has a horizontal asymptote at y equals 0, okay? 1 x over x minus 2, same thing. The degree of the numerator is 1. Oh, that was it's x to the 0, sorry. 1 over x minus 2, same thing as the first example. So I throw a minus 2 in there. All that does is shift the vertical asymptote. Because what's the vertical asymptote for this first function? That vertical asymptote is 0. What's the vertical asymptote over here? This vertical asymptote would be 2. So those two examples are the same thing, really. It's just the second one is translated 2 to the right, and it's minus 2, so it moves to the right. You guys should know that from Algebra 2. We talked about translations earlier in this year as well. So notice are all of these. The last example, the degree on top is 2. The degree on the bottom is 5. 2 is less than 5. If you have a rational function and the degree of the top is less than the degree of the bottom, the horizontal asymptote occurs at y equals 0. Rule number 2, what if the degree of the numerator is equal to the degree of the denominator? Because the next thing that should happen, and I'm trying to talk really fast so I can get through this because I know you guys are tired of watching the videos. You might think, well, rule 1 says the numerator is less than the denominator, but that doesn't have to always be true. Can't I make up a function where the numerator's degree is more than the denominator's degree? Like, look at this last example down here. Right? If I were to make them, if just reciprocal that fraction, it wouldn't be the same rule. So something different has to happen, right? And so it could be that the degrees are the same, and that's what you're seeing on rule 2. Or it could be that the degree of the numerator is greater than the degree of the denominator, and that's what you see on rule 3. So when it comes to horizontal asymptotes, there's kind of like 3 things that can happen when you have rational functions. When the degree of the numerator is equal to the degree of the denominator, it's as if that fraction is growing at the same rate on the top and the bottom, okay? So imagine like you have a pizza, okay? And your friend shows up and he brings a pizza. And it's like, hey bro, let's eat pizza. And you're like, okay, you each get to eat a pizza. And then like 10 more friends show up, but each one of them bring their own pizza. So at this point in time, like the amount of pizza that you're getting doesn't go to 0. You each get to keep like eating your pizza because everybody has the same amount, right? So when the degree on the numerator is equal to the degree of the denominator, the horizontal asymptote ends up being a ratio of the degree term coefficients or the leading coefficients. And the word leading is kind of misleading here because leading does mean that it's in standard form. The polynomial is in standard form, meaning the highest power comes first, and then the next highest power, then the next highest power. So sometimes you'll see these problems that gets tricky, or even when I make them up, I'll make them tricky on purpose. Like I'll switch the terms around. So you got to make sure you're looking at the degree term. So you see this second example here is 2x plus 1 over x plus 2. The degrees are both 1 on the top and the bottom. So the horizontal asymptote would be at 2 because you take 2 divided by 1. 2x divided by 1x is 2 divided by 1. You divide, you take a ratio of their coefficients, the degree terms coefficients. So you have 3x squared over 2x squared. Notice the degrees are the same. 3 over 2 is the horizontal asymptote. It literally is that easy. You just like pick out the numbers and write one over top of the other. So the horizontal asymptote is at 0 when the numerator is less than the denominator. The horizontal asymptote is a ratio of their coefficients when they are the same degree. Now, what if you switch it? What if more and more people keep showing up at your house, but you have this like amazing pizza machine and it keeps spitting out more and more and more pizzas? And if you can make more pizzas than there are people, right? You would pretty much be a hero. We could stop like world hunger and everyone would have pizza. That would be amazing, right? So rule 3, if the degree of the numerator is larger than the degree of the denominator, there's no horizontal asymptote, okay? It goes to infinity. It's almost like if you think about just the parabola y equals x squared. I could squeeze that in here as an example. We have an example. Do another example right here, rule 3 example. Oh, I got to use this. Rule 3. Like, remember y equals x squared? We said, well, that's a parabola. It doesn't have a horizontal asymptote. As x gets bigger and bigger and bigger, y gets bigger and bigger and bigger. But make it a rational function, right? It's x squared over 1. And 1 is actually x to the 0. So this follows the same rule. The degree on top, 2, is bigger than the degree on the bottom, which is 0. There isn't a horizontal asymptote, right? It's almost as if the graph just going to infinity, it's bounded by nothing. So now a parabola is not really a rational function because it's just x squared. So it doesn't have any asymptote at all. But what can happen if you have a rational function with a degree of, say, 3 on top and a degree of 2 on the bottom? Okay, so this is another wonderful example of why we need to know draw the line, change sign, make a rhyme every time. If you have a degree on top that's higher than the degree on the bottom, you can actually do long division. And in this case, you would have to do long division because synthetic division wouldn't work because your divisor is x squared plus 2, not x plus 2. Remember, with synthetic division, you have to have a linear divisor. This is a quadratic divisor. So the denominator is what you're dividing by. Has to be linear, not, in this case, quadratic. So when I do long division, it turns out this ratio, x cubed plus 3 over x squared plus 2, it's the same as y equals x plus negative 2x plus 3 over x squared plus 2. Right? And why is that? Remember, you draw a line, change time, make a round. You end up over here with negative 2x plus 3 is my remainder. Since negative 2x is a smaller divisor, or a smaller degree than the divisor, x squared plus 2, then that's my remainder. And so if you think about this function here, the one with a red box around it, it's like the function y equals x. And as x gets bigger and bigger and bigger, what would happen to this term right here? What happens to this ratio as x gets bigger and bigger and bigger? This is actually rule number 1 of our 3 rules that we just wrote. Notice the degree on top is a 1, the degree on the bottom is a 2. And as x gets bigger and bigger and bigger, this would go to 0. Now, it never actually equals 0, but it gets closer and closer and closer and closer to 0. Its limit is 0, okay? And so this function, x cubed plus 3 over x squared plus 2, literally turns into, basically, it almost turns into y equals x, okay? And I actually have this one graphed. I put this in the calculator before we got started. Let me just start it over, though, because I was messing around with it. Sorry. Zoom 6. Actually, no, don't do that. Let's go to y equals. I'm going to turn off 4. Clear that out. Zoom 6. Here's the graph just to see it. It looks like a line that got hit with a bat. And so now it has this massive, like, welt on it, right? It's like swollen. Here's the function, right? X cubed plus 3 over x squared plus 2. Notice this is another example of a rational function that doesn't have a vertical asymptote. There is no vertical asymptote here. Okay, no vertical asymptote. But it's a diagonal line. It almost just looks like a line y equals something. If I were just to ignore this little bit in the middle, right? I put into y equals the other version. Notice this other version is x plus. So we have blue and red. Go back into Zoom 6. It'll graph the blue one. Right on top of it, it graphs the red one. Okay, so those two equations, a y1 and y2, they are the same equation. Okay, when I do the long division, I get the exact same thing. And what I had down here in pink earlier that I erased was just y equals x. So this is the diagonal asymptote, or what we call a slant asymptote. So when the degree of the numerator is greater than the degree of the denominator, there isn't a horizontal asymptote, right? If you look at this blue curve, notice this blue curve doesn't appear to flatten out horizontally, right? It never flattens out. It just goes up and up forever to the right and down forever to the left. It looks more like a vertical, like a diagonal line, okay? And so this obviously doesn't have a horizontal asymptote. So it depends on the question. If the question is, what is the horizontal asymptote? You would say it doesn't have one. If you're asked, what is the asymptote? You could find the equation of the slant asymptote, which is this pink one, y equals x. Now here's another example of uh, an asymptote, or I should say a graph crossing an asymptote. That can happen. Let me zoom in for a second. You see the pink curve. It does intersect the blue curve, right? The pink line. So sometimes a graph crosses an asymptote. And what is happening is, you see, as x gets bigger, the blue part is below the pink part. The blue part is coming up toward the asymptote, whereas as x gets smaller, the blue part is going down towards the asymptote. So if I were to zoom out 3, here's the original graph. It does cross, the blue graph crosses the pink graph. And so if I were to trace, like let's just go to trace, and I'm on the blue curve and let x be 9. So the actual function's value is 8.81, right? 8.81 is the actual function's value. Obviously, if I go to y equals x, go up to the pink one, and put in 9. Oh, look, when x is 9, y is 9. And 8.8 is pretty close to 9. So the blue curve and the pink curve are really close to each other. If I zoom out again, zoom 3. Oh, man. But I want to zoom out from 0. I don't want to zoom out from there. Hold on, I got to move the cursor. See, I don't know if you've ever used the zoom out function much. It zooms out from whichever point you have the cursor at. So if I were to leave it at like 9, 9, I want to zoom out from 0, 0. Boom. That's when I zoom out here. The blue curve, I did something. I hit enter again. The blue curve, the little bump in the middle is harder to see, right? You zoom out and you can't tell that, oh, look, there's a zit on your face, right? um, so, and if I zoom out again, the blue curve looks exactly like a line. The pink curve pretty much goes exactly on top of it. You can't even see the blue line anymore. So the blue line, as x gets bigger and bigger and bigger, slowly turns into the pink line. Now, technically, they never touch. Technically, these two curves don't touch, except at the point where they do cross. Right, the blue curve crosses the pink curve. Should have said they don't touch. But as asymptotes, as x gets bigger, it doesn't touch. So if I were to trace, I don't know how big this number is. Can I go to 100? Yes. So look, on the blue curve, when x is 100, y is 99.98. And obviously, if I go up to the pink curve, when x is 100, y is 100. Oops. Anyway, okay, so I'm about done. I've talked too long. Get rid of this picture. So this rule number 3 is kind of tricky. There is a lot to it. When the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. There is a slant asymptote. If you're ever asked to find the equation of the slant asymptote, you have to do long division. Another application of long division. There's lots of these in upper levels of math. The slant asymptote is just the y equals x part. Okay, that's the asymptote. Remember, because this remainder part, as x gets bigger and bigger, goes to 0. So that term basically disappears. So the asymptote, the equation that the curve is getting closer to, is basically the long division minus the remainder. You just throw the remainder part away, right? It's just this x part. That would be the equation of the slant asymptote. Now, this assignment, I did not push for slant asymptotes. I just pushed vertical and horizontal. So hopefully this has been a good review of vertical and horizontal. If you need to go back and pause the video because I talk too fast, or maybe I talk too slow, and you're like, no, I watched this video at twice the speed so I can get it over with faster. But that's funny. Then, if you need to write the notes down, here you have 12 problems. I pulled this from some other random algebra 2 book. These were rational functions. I think you're supposed to graph them or something. And I was just like, all right, let's just talk about asymptotes. So You have rules for vertical asymptotes, and you have rules for horizontal asymptotes. Again, if there is no horizontal asymptote, say no horizontal asymptote. You don't have to do the slant asymptote unless you're really bored. Go ahead and do the long division. Maybe I should have said do that, but I didn't do that on my answer key. Anyway, I will post these questions, these 12 questions, as a JPEG so you can look at them, but they're here at the end of the video as well if you want to just pause it here and work these out. Anyway, I hope you've had a fun time. I know I've had a fun time. I tried to go as fast as I could. I probably didn't go fast enough, but I love you. Have a beautiful day. Peace.